Yeah, thank you very much, Professor Nisai, for the kind introduction. And it is really my great pleasure and privilege to be here again after this dark time of COVID-19. In Germany and Europe, we also returned more or less to normal. And yeah, so this makes it again possible to travel. Many things are good via digital media, but not everything, and therefore it's good that we also have the opportunity to meet here again. So for the seminar today, we choose a topic which is of quite a high relevance with regard to the change of the energy system. So one of the big questions is when we are going into the transition of the energy system, we know quite well how to serve the electricity sector with renewables and so on. The technologies are there. But beside this, for sure, we will also have applications where it is either questionary, or it's a question if we may use batteries and electricity or direct grid connection, or if we need something like fuels, molecular-based fuels as we have them today, based on oil, based on gas. And the point is we can produce such substitutes from hydrogen. We can produce gas, methane. We can produce liquid fuels. All this is possible. But the problem is infrastructures are not there, and it also costs a lot of energy. So the efficiencies are relatively low. And therefore, it is extremely important to check very carefully, first of all, what are the technologies, how far are they available, especially also in the coming years. Everybody is talking about the world hydrogen economy. The point is, there is nothing about this right now. So the question is, how fast can it be ramped up? And for which applications we may use the hydrogen first, as soon as we have some. And this is all what I would like to look at today, starting with a look into general points about climate change, just to remind us here the implication, what this all means to the energy system, what means an energy system mainly dominated by renewable energies. I also will make a short remark on so-called negative emissions. So taking CO2 out of the atmosphere, because it can have also significant impact on the future concepts. And then going into the other things, questions, efficiency with regard to CO2 reductions, what is about battery and fuel cell, electric vehicle market, state of the battery technology, and then infrastructures, and especially then hydrogen, properties, transport, production of hydrogen and eFuels, and also some discussion about different applications, and finally maybe some political implications, because this will all lead also to very strong changes in industry politics, but also in energy flows and capital flows and so on. So therefore, I would like to start with having a short look into the general issues on climate change and the demand for lowering CO2 emissions, because this is for sure the driver for all of this. And I would like to give you some insights into European and German strategies here especially. And they are quite similar in the United States, for example, whereas their approach is different. So you all know probably these fiber curves of the climate. This is now I have to check if this technology is working here. Okay, yeah, so okay. So this is the CO2 concentration in the atmosphere. It is measured on Hawaii, and it's the longest timeline we have since 1960. And you can clearly see there's only one direction of the CO2 emission, even though we are talking since 1990 in world climate conferences on reduction of CO2 emissions. We are not there at all. Yeah? So we still have a significant increase in CO2 emissions, as we can see here. Beside this, and this is sometimes overlooked, CO2 is only one of the climate gases. Methane is a much stronger climate gas and contributes about 25% to the worldwide global warming. And here as well you can see still an increase in methane concentration in the atmosphere. Furthermore, if we look to what really happens from this, the temperature increases. So we have, meanwhile, more than 1 degree C above the pre-industrialized times. And it is, meanwhile, very clear for the climate researchers that the 1.5 degree centigrade target, which was defined in the 2015 climate conference in Paris, cannot be met anymore. So there is no way to meet the 1.5 degree target, at least not in the coming decades, maybe towards the end of the century, if we are really going also for negative emissions and more. But the temperature will rise, and one of the outcomes is, for example, also increase in the sea level. You can see within the last 200 or 150 years, the temperature, the sea level rised about 25 centimeters worldwide. But what is especially important is, that the rise increases quite significantly. So the sea level rise accelerates. So this is just one of the outcomes. All the other things you know, more floods around the world, more storms, less ice, and so on and so on. And this is just how it looks like. As I said, since 1990 we have world climate conferences, but the CO2 emissions still significantly increase on a worldwide level. We are not, probably not even at the peak right now. We hope that the peak appears before 2030, but the problems are very clear and severe, so lots of things need to be done, and some areas in the world, such as Africa or maybe even India, have just started to grow their economies significantly. So if we cannot manage to transfer them right away onto a CO2-free energy supply, we'll get in even more trouble. When we look how these emissions are distributed worldwide, we can see that this is very unevenly distributed. We have extremely high emissions here, especially Australia and North Africa per capita. Europe is also among the very high emitting countries, but for example, meanwhile, the emissions per capita in China are pretty much the same as in Germany. 7.5 tons per capita is the CO2 emissions in China as well as in Germany. So this has leveled in the last years almost. So then when looking where these emissions come from, we can have a look into the different fuels. We are using the different fossil fuels, and there we know that different fossil fuels have different specific CO2 emissions, no question. And this is one of the reasons why many were putting lots of emphasis to increase the share of natural gas. So natural gas was planned to be the technology for the transition from the, let me say, old fossil economy to the future renewable-based economy. But especially in Europe, we suffered a lot with regard to gas. As you all know, we have since, tomorrow, since a year, I think, this war of Russia in the Ukraine. And as a consequence, European Union mainly stopped the imports of fossil fuels from Russia, and especially Germany was very much dependent on this. We imported more than 50% of our natural gas via pipelines at very low prices, we have to say, from Russia in the past. This is now over. We also do not import oil or coal anymore from Russia, and this needs all to be substituted. And this is for sure one of the main reason why gas prices and therefore energy prices in general increased so much last year, because Europe bought a lot of additional gas, LNG gas, on the world markets, and by this the prices rise dramatically. Meanwhile, we're quite optimistic that we will get through the winter without major problems with gas supply, but the next year will be as challenging as this year. Therefore, the increase in natural gas consumption as an intermediate technology is now very questionable because of the high prices. On the other hand, coal especially emits 70 to 80% more CO2 per kilowatt hour thermal energy, and therefore gas is still a good idea, but yeah, if it's not available or very expensive, we have to look for the alternatives. If we look then to power generation, we can have a look here, what are the specific emissions. We see that the highest emissions come from lignite, and lignite is the cheap type of coal. This is more or less the only natural resource we have in Germany. Just next to Aachen, there are one of the two large centers for mining of lignite coal, and we have, I think, something like 8 to 10 gigawatt of lignite coal power plants about 60 to 80 kilometers around Aachen. But they have by far the highest emissions. So there's more than 1.2 kilograms of CO2 emissions per kilowatt hour of electricity. And if we go to natural gas, and this is only the single cycle natural gas power plants, if we go to combined cycle, so gas turbines and steam turbines, the emissions are even going down to something like 450 grams of CO2 per kilowatt hour. So gas is generally a good idea, but expensive as a fuel, and therefore we have to go for this fuel switch. So one more point I would like to show here is that the question what really contributes to climate change is very complex. And this is just an example. This is from air travel. The airplanes for sure emit CO2, no question. Flight from Frankfurt to Bangkok roughly emits 1 ton of CO2 per passenger on the airplane. But this is not all what contributes to the climate warming, to the global warming. You can see here, and I don't want to go into the details here, but we have nitrate gases, water vapor, soot, sulfate, particles, and lots of them have, on the one hand, additional global warming potential, but some of them also reducing it to a certain extent. But what you can see is, depending on the studies you're following, the global warming potential from a CO2 here marked as, or taken as 1, is in total somewhere between 1.9 and 4.7, as I said, depending on the studies you're taking here. And this means, especially the water vapor is here a very critical thing, reducing the CO2 emissions of an airplane maybe even to 0 by using, for example, biofuels or synthetic fuels, things we are talking to today, will not reduce the climate, the global warming potential of flying to 0. Because, for example, if you would use hydrogen or any other fuel, it will still emit water vapor, for example. So this is not going away. So the complexity of all these things is very high, and simple answers are not there. But we have to be aware that besides what we typically have in mind, like passenger cars, power plants, and so on, we have in the global transport sector significant emissions, for example, in the shipping and in the aviation, about 1 gigaton per year. Both contribute somehow like 3% each to the world emissions. And I'm putting emphasis on this because it is very clear that such airplanes will not fly from continent to continent on batteries. At least, I'm sure, not within my lifetime. And I hope to live some more years. Yeah? And we also will not see these large container ships traveling around the world on batteries. Yeah? So these are definitely applications where we need alternatives to today's fossil fuels. We have to supply them with new synthetic fuels or e-fuels, however you may call them, or directly hydrogen use. And this is what I would like to talk about today. Yeah, so here it becomes very obvious. You may fly such a plane from one country to another, but then on battery, but then it is filled only with batteries. 100% cargo is battery, which makes obviously no sense. So this is the reason why we have to talk how we can get clean fuels, clean gases, and this is where I put the focus on in today's presentation. Looking to the policies, we are all still following the last very important agreement on the World Climate Conferences from Paris in 2015, where the 1.5 degree target was agreed on. But as I said, maybe already in 2015, but meanwhile definitely it is clear we cannot meet it. So we will go beyond 1.5 degrees C without any question. But nevertheless, based on this treaty here, the European Union, for example, has set itself the goal to be CO2 neutral latest in 2050. So seems to be still a long time ahead, but it's just 27 years to go. So that's not a lot at all. And in Germany, also due to because our court, our constitutional court, pushed the politics to go even faster. We are planning for the CO2 neutrality already in 2045. So this is where we would like to get to, and especially until 2030, there should be already a reduction in CO2 emissions by 65% compared with 1990. And this is extremely challenging. And how challenging it is, you may see from this timeline. These are the CO2 emissions from Germany, starting in 1990 here. And you can see there are reductions in emissions, and they are unevenly in the different sectors. So the largest contribution comes from the energy sector, because we have meanwhile almost 50% of renewables there. But in the mobility sector, for example, and I will come back to this some more times, we have no progress at all. No savings in the mobility sector yet. But what really becomes then challenging, you can see here, these are the targets. So 2030, minus 65%, 2040, minus 88%, and then 2045, the climate neutral, or the CO2 neutrality. What this means, neutrality, I come back to this in a minute. The challenge, for me, the biggest challenge are not the targets in 2040 or 2045. The biggest challenge is 2030, because the time until 2030 is getting extremely short. And we again lost more or less the last year, because our politics were very much busy with solving these short-term energy problems, which we achieved due to this Russian war in the Ukraine, and therefore time is running. Yeah? So this is the most challenging thing. We have also to be clear that even these ambitious timelines here are not sufficient to meet the 1.5 degree target, and probably not sufficient to meet the 2 degree C targets, even if the whole world would follow us on this timeline. And it's becoming even more clear how challenging these targets are if we look to different sectors, because then it becomes more clear what it means in detail. Yeah? So this is the basis for our actual Climate Protection Act. And here we can see that just from 2020 to 2030, the industry should save about 37% of the CO2 emissions, the energy sector more than 60%, mobility and buildings about 40%, and agriculture 20%. Yeah, so these are the challenges, and they make significant changes on a very short time scale necessary. To achieve this, the government, which came into power about 1.5 years ago, they put some actions on their action plan. The first one is to come to an electricity generation of 80% from renewables in 2030. So in 2020, 21, it was about 50%. So increasing this to 80%, while at the same point of time, we expect an increase in the electrical power demand. So in 2020, it was about 545 terawatt hours, and now we expect, due to the additional demand from the mobility sector, electric vehicles, for example, heating with electricity and heat pumps, but also hydrogen production, we see an increasing electricity demand towards 2030, and then further increasing towards 2040, 45, towards maybe 1,000, 1,100 terawatt hours of electricity demand. And this makes it challenging in a double way. It's not only increasing the share from 50 to 80%, but the share of 80% of a significantly increased amount of electricity. Yeah? And this requires a very strong initiative to increase investments in wind turbines and in PV systems. And our Chancellor just said it would be necessary to have every week, I think, every day, 4 to 5 wind turbines in the future. So, which have to be built new. And this is challenging, definitely. At the same point of time, electrolyzer capacity should be increased to produce hydrogen. This is what we are talking today about, mainly talking today about. Then in 2030, about 80% of all new cars should be zero-emission vehicles. Whereas, meanwhile, the European Union have defined a ban of all new combustion engine cars from 2035 onwards. So beyond 2035, you won't be able to sell any new combustion engine car on the European market. So these are all things which cause very fast changes in industries. If we look where we are, when we look to the European Union in total, we can see this is still at the beginning of this major transition. So the power sector in total has a renewable share of about 30% in the market, decreased for sure since 2017 further, but still not too high. But we can see the electricity sector, same like in Germany, is quite good with renewables. But the other sectors like heat and transport are significantly lower and need much more change in the coming years. And these are the numbers for Germany, for 45%, 50%, in power generation, but only 7% in the transport sector and about 15% in the heat sector. So heat sector in Germany is the largest energy consuming sector because we have cold winters. So we have to do lots of heating. Therefore, we are losing less air conditioning in the summer maybe, but heating is really of major concern. And heating of the houses at this point in time takes place roughly with more than 80% from oil or from gas. Direct burning gas or oil in the houses, and this is most challenging here. So long ways to go. This is a relatively share of the emission, and I'm just showing this because on the one hand we achieved the 40% reduction in emissions from 1990 to 2020, but I would like to put emphasis here on the central dark red part. This is a share of the mobility sector, transport sector. It was about 13% of the emissions in 1990, and due to the fact that the absolute emissions almost did not decrease, we are meanwhile at about 20% share in the transport sector, whereas in other sectors like the energy sector, so power production, the emissions reduced, not only in absolute numbers, but especially also relative. So transport sector is of major concern, and therefore lots of discussions are going on here, especially what kind of fuels, what type of propulsion systems should be used here in the future. And just to show additionally how difficult it will be to achieve these the CO2 reduction targets, I made this very simple calculation. It assumes that the share of the newly sold passenger cars increases from now a relatively small market penetration to 80% in 2030, and latest in 2035 to 100%. This is the green curve. So the share of newly sold cars which are emission-free. Most probably mainly battery electric vehicle, could be also fuel cell cars, not very likely, but possible. But even then, if you look to the green curve, this is still the stock of the remaining passenger cars with combustion engine, as long as we are not taking them out of the market, taking into account a 15 years life periods. So you can see that even if we achieve the 80% new cars in 2030 and 100% in 2035, in 2045, when we want to achieve zero emissions, there are still conventional cars on the roads. And either you take them out of the market, probably then the government has to pay money to the people because you take them the cars which are not at the end of lifetime, or gasoline must be extremely expensive so that the people more or less on their own would reject these cars. But the times and scales are long. So it really takes time until we can change such a system. And every year, every day, we are losing in staying with these target lines. We will have more problems towards 2040 or 2045. Thank you. Yep. Right. So yeah, this is Germany's power mix in 2020. The share of renewables varies from year to year. Many thanks. Especially because wind and sun are fluctuating, so sometimes we have good wind conditions in a year, sometimes we have good or better or worse conditions in the PV sector. Therefore, it varies somewhat, but you can see that the majority still comes from winds here. The light blue, this is onshore wind turbines. This green here is offshore wind, and then we have photovoltaics and biomass. And biomass and photovoltaics for the first time were leveling in 2020. Biomass is slightly reducing in the future, and or maybe more heavily reducing in the future, whereas photovoltaics is growing relatively fast. Generally, we expect that the growth in photovoltaics will be larger than the growth in wind, but both are very important. So especially for the German energy system, the combination from wind and PV is important because sun is good in the summertime, and the wind especially is much stronger in autumn and winter time. So we can compensate the lower solar radiation in the winter half of the year by better wind conditions. So both together give a relatively good power supply throughout the year. Yeah? Just putting all on wind or on PV would cause lots of problems because then we have to store lots of energy from winter to summer or from summer to winter. And these are now the targets for the installation. Yeah? So these are the targets which were set by the government. For sure, these are just targets because in a political system as ours, the government itself is not installing anything. Yeah? So they just can try to optimize the legal frameworks and maybe give some subsidies and so on. But at the end of the day, for sure, these systems need to be built by companies. And you can see here that we have latest in 2028, something like 20 gigawatt of photovoltaics should be installed year by year, and in addition another 15 gigawatt of wind, and these ramp ups from quite low starting points in 2021, 2022. This is the main challenge, and it's not only a challenge to build up the industry, or to grow the industry, or to buy these things. At the moment we buy most of the photovoltaics, for example, from the Chinese market, but it is especially also a problem with availability of craftsmen and sites. So it takes long years typically to develop new sites to set up this, and this is especially where our government is targeting. Each city, each village should define at least 2% of their land area for renewables. So to make sure that we have sufficient area for this. And then if this all would be installed, then we would come up with a capacity of, in 2030 already, of about 360 gigawatt of installed renewable capacity. And this is worth mentioning because at the moment our peak electrical load is at 80 gigawatts. So this means in many times of the year we will have very significant surplus power generation, and this for sure is what gives us room to take this surplus energy to produce hydrogen from this, and then in a second step e-fuels or methane or whatever. Yeah, so very significant technology, flexible, this requires for sure lots of flexibility technologies like storage systems, like controlling the loads in vehicles, in industry, but also here hydrogen production as just mentioned. So all this for sure has significant implications of the change of the energy system. So the energy system will look totally different in a few years compared with today. Some new players may come in place, but especially also capital flows around the world will change, because we may buy in the future hydrogen from somewhere in the world rather than oil or gas, whereas there are other countries in the world which may supply hydrogen compared with gas and oil these days. So business models which were valid in these days may change in the near future already. And just to remind us what this really means, the change we are just undergoing is, until now we're using fossil fuels, which are at the same point of time perfect energy storages, and the vast majority of this we then burn. So we produce heat from it. We take the oxygen from the atmosphere and we burn it and we make heat. heat in a combustion engine, heat simply in a heating system, or heat in a power plant to produce steam, or to operate a gas turbine and or steam turbines and so on. But this is what we typically do, yeah? Which is quite a pity, because heat is, let me say, has the lowest value among the different energy carriers we have. Yeah? But this is the way how more or less all our systems work today. And what comes is that our main source will be electricity. Yeah? Mainly from wind and PV systems, most probably. Some people would add here maybe some nuclear power technologies. This could be discussed. Anyhow, they also produce electric power. And that's an important thing. Yeah? So whereas here heat is what we put into in most of our processes, here it is electricity. The electricity has a highest value, because with electricity you can do everything at very high efficiency. Yeah? You can drive electric motors with more than 90% of efficiency. You can put it into heat pumps to generate heat with efficiencies of 300, 400, 500% in a heat pump system. You can use it for communication, or you can transfer it to heat just by ohmic resistances with 100%. Yeah? So electric power is extremely flexible, and this means once we have electric power, we also should look very careful which applications we can shift directly to the use of electricity. And that's the main motivation for building electric vehicles, battery electric vehicles. Battery electric vehicles are not better in a certain way than combustion engine cars. Combustion engines are really masterpieces of engineering work, no question. But we cannot get them CO2 free easily. And if we have electricity, it makes sense to think about using it as efficient as possible. Nevertheless, beside this, we again will also need some hydrocarbons or some liquid fuels which we can put, for example, into the airplanes or into the cargo ships. And then the question is it necessary then to put them also into passenger cars, or to put them into trucks, or into farming machines, or into construction site machines? These are all the open questions. Where we definitely will need hydrocarbons is, for example, for the chemical industry. The chemical industry uses oil mainly, and smaller amounts of gas, not for energy purposes, but as a raw material for plastics, for example, but also for medicine and whatever. So there are 500 million tons of oil per year worldwide, which are used simply as a raw material in chemical industries. And all this needs to be replaced, and I will show you later on some numbers what this really means if we want to generate all this from electricity via this pathway. Electricity, power, and then producing hydrogen, and finally these hydrocarbons. But it will be absolutely necessary, and the big fight at the moment is not about the question, do we need hydrogen, do we need e-fuels? Yes, we do. The question is, which sector may get some? For example, the steel industry would need huge amounts of hydrogen to convert from, to convert the processes for producing steel from today, the very CO2 emitting processes, towards green steel. So if you want to build such new steel factories, you would need right from the beginning huge amounts of hydrogen. And the energy sector becomes more complex. So we get, whereas we had in the past quite separated energy sectors for electricity, for gas, for heat, for fuels, and so on, we're now getting a very much interlinked system. We have the power generation here mainly on the side of the electrical power, and from this energy goes into the heat sector, but it also will go via electrolysis into methanization, hydrogen. We have seasonal storage and gas most probably, And from the seasonal storages, we can produce also electricity during winter times. All this is extremely interlinked, and this also makes this transition extremely complex, because there are very few also engineers and people from economy who are familiar with all of these sectors at a time. But you must be able to think in all of these things, because one of the questions is, if there is a surplus of electrical power generation, for example, where to store it? Will we store it directly in some electrical storage systems like batteries or pumped hydro, or will we transfer it directly to the heat sector, because maybe we need heat or cold in the winter or in the summer? Or do we produce gases and put it into the gas sector, or do we produce fuels? So all of these things are of relevance, and in addition, all of these systems are limited also by their infrastructures, by their grids. So which infrastructure should be enhanced in the future, which might be not that relevant anymore? For example, as I said, at this point in time, we are heating about 50% of our houses with gas. This means we have a very elaborated gas distribution system where most of, 50% of the houses are connected to a gas distribution grid. It is quite likely from this point, from the view of this point of time, that this gas system will not be needed anymore in the future, which is a big problem for those who have invested. It's maybe stranded investment, but it especially also the question, where do we invest right now? So all the things have timelines of decades. So if you install an infrastructure, you would like to operate them for 30, 40, 50 years, and not only for very short times. And all this comes together with questions about digitalization, energy law, resources. So will we be limited in some of the new technologies by mining resources, for example, is one of the key questions. But also the future energy system will still rely on a worldwide trading of energy carriers. Densely populated countries, especially more in the north, like Germany, like France, like Great Britain, most probably will not produce the energy they need in the future on their own area. So we will need to import either electricity via transmission lines, maybe from the southern part of Europe, gases, either by ship or by pipelines, or we will use fuels and hydrogen coming from somewhere, maybe from more sunny regions in the world, like Africa or Australia or wherever. These are new opportunities for those who can offer these energy carriers, but it also requires new infrastructures, new type of ships, new type of harbors, but also all the legal frameworks are not there yet. So there are no international legal frameworks, for example, for hydrogen ships and for harbors where you may bring hydrogen to. So therefore, there are several very important areas of application in which hydrogen and its derivatives are really indispensable from today's perspective. For example, if we have wind and sun fluctuating seasonally, we need long-term storage. And this will be gas. Gas coming from hydrogen first, maybe then methane. We will remain an importing country, and probably most of the more industrialized countries will be. So we need transportability of energy over long distances. We need hydrocarbons as a basic for the chemical industry. So we need synthetic hydrocarbons. We have the transport demand over long distances remains, probably with synthetic fuels. Not easy to transport hydrogen directly. Also something we will discuss further this day. And we also will need high temperature heat, for example. Low temperature heat is easy to make with heat pumps, high temperature heat in the range of 1,000 degrees centigrade or more for some industrial processes is even more difficult. And here we need, again, replacements for gas and oil based on some type of fuels. And at the same point of time, building up such a hydrogen-based economy possesses a lot of challenges. So the first question is how can we support first movers? Right now, one of the biggest problems is all the technologies, the renewable power generation, but also electrolyzers and the technologies to produce from hydrogen, then fuels, methane, and so on, are still expensive, and they will show decreasing cost. But this means the ones who invest today pay more for their production facilities than those who will invest tomorrow or the year after, and so on. And therefore, just from an economic perspective, there is no perfect time to do investments. Because you have the perfect market, and if somebody can produce cheaper, he simply will take the market. That's a big difficulty. So the question is, how can we support these early movers that their investments will not be stranded if in 5 years somebody is producing the same hydrogen at half of the price, maybe. Then the transport options for hydrogen and its derivatives are not yet developed in many areas. So we don't have harbors which can ship liquid hydrogen or something like this. So this needs to be developed and costs a lot of time. Then we have to face a lot of losses. We produce electricity first, but if we generate hydrogen and then maybe even further liquid fuels from this, so for replacement of oil, this costs a lot of efficiency, and therefore we have to analyze very carefully where we should take these losses into account and where it is more efficient to use this electricity maybe to save CO2 in a different place. For example, let me give an example. Morocco, in the northern part of Africa, has a lot of sun, and a lot of people in Europe think Morocco would be a great country to produce based on photovoltaics or also wind, because on the shorelines they have very good wind conditions, to produce hydrogen for the European economy. Not a bad idea, maybe even for Morocco a good business, no question. But the power supply in Morocco at this point in time relies more or less 100% on fossil fuels. So if we produce electricity from wind and PV in Morocco, we would save much more CO2 emissions if we take this electricity and replace the existing coal, gas, and oil power plants, rather than going via a very low efficient way to use this same electricity instead to produce first hydrogen and maybe then some other hydrocarbons to burn it maybe later on in a passenger car. So this, I will show you numbers on this in a minute. From an overall global climate perspective, it makes no sense. So we should start to export hydrogen from renewables from Morocco once they have converted their fossil fuels power generation to renewable energies. Not earlier than this. But business may drive different stories, but CO2 emissions are globally. So at the end of the day, if we want to save the climate, we want to reduce climate warming, we have to think globally and not about the emission of a certain country. It would reduce Germany's emissions if we import Moroccan hydrogen, but the overall emissions would be reduced significantly more if this electricity in Morocco would not be used for hydrogen, but for reducing their gas and oil power production. Furthermore, the green hydrogen are more expensive than fossil fuels. Question is, maybe the increasing gas prices are somewhat a game changer now. And the green hydrogen production capacities are still very low. I will also show you within the day some numbers from the International Energy Agency where we are today with the electrolysis capacity and where we have to get to in the near future. So lots of challenges, and all is what we are going to talk about here. So this brings us to the question of, or what it means to have an energy system which is dominated by renewable power generation. Yeah? So this is how the renewable power generation evolved since 1990 until 2020. You see the numbers we have seen before. Wind power with the highest share, biomass and photovoltaics quite equal. Geothermal energy does not really play a role, and Germany has a very limited potential for hydropower. Yeah? So that's about just 3 to 4%, and there's not much potential to increase this. This is for sure different in different countries of the world, but this is as it is. Photovoltaics, meanwhile, is available in huge systems, as you know. This is a smaller one in Germany with 3.8 megawatt. This is one in China with 850 megawatt of photovoltaics. And this is a park which is just under construction in Dubai. And this will have at the end a capacity in the order in total here of more than 2.8 terawatt of power generation from photovoltaics. So this is not a small technology anymore. And why does this happen? Simply, meanwhile, lucky we are, renewable power generation is the cheapest way to produce electricity among all the other alternatives. By far cheaper than using gas, cheaper than in most of the countries than coal, and by far cheaper than power production from nuclear power plants, at least if you have to build the nuclear power plants new. So this is a good news. Yeah? So this is more or less what we achieved in the last, let me say, 20 to 30 years to develop new technologies which are now in place, and wherever you really make decisions based on pure economics, the renewables are in the forefront. So we must not convince people anymore about the technology. This is mainly due, as I said, due to the reduced prices. We know there is economy of scale depending on the overall amount of installed capacities. The pity is the vast majority of the production capacities are concentrated in China. That's not a problem on its own, but it's a pity that we do not have a more widespread technology all over the world, because we would need even more capacity than what we get today. And yeah, that's maybe something which has to develop in the near future again. And it also can be seen that, and this is important for all the discussions, because there are still a lot of people who always say renewables make our energy system expensive. Yeah? And this is not the case. Yeah? And these are numbers from the German energy market. This is the first part of 2020 in Germany, January to mid of September. And each of these yellow dots here is a price from the power exchange, from the German power exchange. Yeah? So every quarter of an hour, a price is set on the power exchange. And it is plotted versus the actual feed-in of renewables. So wind and PV here are shown here. So for example, here we have 25 gigawatt of wind and PV feed into the grid. And we can clearly see that the price at the power exchange decreases with increasing share of power generation from the renewables. Yeah? And the trend line here is very clear. Yeah? So we are most expensive when we have to rely completely here on the fossil fuels, and with high penetration of renewables we are getting cheaper. This is important, especially also from a psychological point of view, because people have to understand So renewables is not the enemy of a cheap energy system. It's the friend of a cheap energy system and the only solution, more or less. And this is especially true in Europe because we have since, I don't know, since 15 years maybe, a CO2 trading mechanism. But for a long while, it did not really work because the price was very low, so it did not have any impact. But in the last 2 years, and many people have overlooked this, because in the last 2 years, due to all this Russian politics, even before the war began, energy prices increased quite a bit. But in parallel, also the CO2 emission trading increased its prices dramatically. So just yesterday, I think, in the European system, for the first time, the ton CO2 was traded at more than 100 euros per ton. That's a lot. So if you produce power from lignite, so the overall production cost in the past was about 3 euro cents for the mining, for the power plant, and so on. So for everything, 3 euro cents. But it emits, simply speaking, 1 kilogram of CO2 per kilowatt hour. And if you have a price of 100 euros per ton, it means you have 10 cents additionally cost on the lignite power generation just for the CO2 emissions. 3 cents is the cost for digging for the mining of the coal and the power plants and all together, and on top you get 10 cents for CO2 price. This is what makes fossil fuels expensive, and it will stay expensive even after the if the war might have stopped or might have ended. This will not go away anymore. So these trading mechanisms are powerful, and more countries adapt this because this is driving with a market tool the change in the energy system. And but nevertheless, I have mentioned it, so we still have to go significantly further to be compatible with the 1.5 degrees C targets here. And just to be clear, the capacities in renewables are not really limited, even though I have mentioned that a country like Germany and others will still remain to import energy carriers in the future. We would be able to do it also in Germany. So just, and therefore I would like to show you a very simple calculation about this, because we already now use significant shares of our land for growing crops for bioenergy. We're using bioenergy as biofuels, 5 to 10% in our gasoline, and we're using it for power generation. And for this, we use in total about 2 million hectare land in Germany continuously for growing crops for bioenergy. In total, we have about 16 million hectares of land for farming. So out of these 16 million hectares, 2 million are used for biogas. Now, the problem is, or if you make some assumptions about the use factor of photovoltaics, the efficiency of PV systems, including losses, and solar radiation as we have it in Germany, we can calculate that if we would convert this area of lands, or if we put, instead of growing crops for energy purposes, we put PV systems on the same lands, we can easily produce something like more than 1,000 terawatt hours of electricity. Today, we use 550 terawatt hours of electricity in Germany. So we could produce double on the same amount of land, and that's quite significant. The main reason is the conversion factor of plants from solar radiation to energy is in the order of 1%. And PV does it with 20%. So from the same land, we can get 20 times more or even more energy. And by the way, we also would do something good for the environment, because growing these crops needs a lot of fertilizers and pesticides and so on. And if we would grow, let me say, PV, then we could leave the land around relatively untouched, and would be a good habitat for insects, for birds and other animals and more. So would be good for all of us as well. But there are also ideas to combine both, farming and PV. This is what they call agro-photovoltaics, putting the PV on some small towers, maybe 4 meters or 5 meters high, so that you still can grow crops below this. And some of the crops even grow better if they get some more shadow. Some may have reduction in production of maybe 10, 20% due to the shadowing, but this is also an option. So I just want to show with this, we are not suffering from area. So we're not having a problem with land. We just have to do it at the end of the day. But what results is for sure a very fluctuating power generation. So this is a simulation for a system with a little bit more than 80% of renewable power generation here. This is 1 week taken out of the European energy system or the German energy system. And if we look to this week, we have very small amount of energy coming from hydropower, an assumed wind generation profile for onshore wind, for offshore wind, and then for PV. So as I said, in a system which is made for about 80%, 83% of overall power generation within a year. So this is then power generation by renewables, and we have a certain load curve. So assuming that it is more or less the same as today, about 80 gigawatt in peak. You can see here always the day times and the night times, and you can see here Saturday and Sunday with a somewhat reduced power demand. And from this we get what we call the residual load curve. So the residual load curve is the amount, is the load, what is here the black curve, minus the power generation from renewables. And this means whenever this residual load is positive, we are lacking power generation. So we have to add power from storage systems, for example, or we have to reduce the power consumption. More flexibility, for example, reducing charging of electric vehicles or use in industry or whatever. And whenever we have negative residual load, it means we have surplus energy. So this is what we can put into storage systems, what we can put into hydrogen production, and then furthermore in fuels and so on. So negative emissions are easy to handle. This is not really a challenge. Positive residual loads are a challenge, because if we cannot manage to balance the loads and the production in any second, then we will have trouble, and the electrical system will break down. But these are the challenge we have to deal with, and this is why we need much more technologies for flexibility, which can deal with this. So this is a major change. In the past, we simply adapted mainly power generation from the conventional power plants according to the load curve. So we always followed the load curve with our conventional power plants, because they have the energy storage in the fuels included. So this is a really great thing about the fossil fuels. They are perfect energy storage systems. So no question about this. And this means for grid stabilization, there are lots of different technologies, but among them, and this is why I just want to point out, are for sure also these electrolyzers, taking electricity from the grid, and depending on the technology, they can also ramp up and down very fast. That's very important, so they can follow really the load curve easily, and help to stabilize the grid on the one hand, but also to take the energy to converted from electricity into chemical energy in terms of hydrogen. And when we look to the demand in energy storage, we see there are different fields where energy storage is needed. We need short-term energy storage, which can balance in the range of seconds or with up to a day. We need energy storage, this is what we get from our calculations, which can serve the grid up to 3 weeks. Yeah? So we see that there could be periods in Central Europe with up to 3 weeks without sufficient wind and PV generation due to very low winds, very low solar radiation in the winter times. And then we have to serve the system mainly from our long-term storage systems. And this will be gas. There is no other chance, no batteries can do this. And the problem is, if you have such an extended period of low wind and low PV, you will have it not only in Germany or only in France or only in Poland, you will have it all over Central Europe at a time. And the first 2 weeks of last January were not a 3 weeks period, but a 2 weeks period which came very close to this. So there was no wind, there was, in the winter anyway, we have almost no sun. So this was very, very crucial. Then we need heat storage, maybe even seasonal storage. We need gas and liquid hydrocarbon storage, and then we need, in addition, the flexibility. So ramping up and down the consumption in industry, in houses, in cars, and so on. And technologies we have available for this are batteries, flywheel, supercaps, pumped hydro storage, and so on. For the short term, we have the gas storage. For the long-term systems, we have heat storage with water from low temperatures up to 100 degrees C, phase change materials, chemical storage, and here we have fuels based on the hydrogen. And finally, here, the flexibility. So we have technologies for all of this. The main reason why they are not there yet is not because we do not have them. It is because right now, there's not a huge demand. Because even at 50% of renewables, we still can balance our grid relatively easily by ramping up and down the remaining fossil power plants. There are still a lot of people and politicals running around and say, we cannot go further with the change of the energy system. We should not install more wind and PV because we have no storage technologies. It's totally wrong. The storage technologies will come if there is a demand, and the demand means if there's a market. And at the moment, there is no market, not for large-scale storage systems because it can be handled by the system. But as soon as it comes, you will see that the storage technologies will emerge because the technologies are all developed. So we can go for this. So this is not a showstopper. And finally, I just want to point out once again, because sometimes people try to make the change of the energy system somehow like a fight between those who say we should go more for an electricity-based system in the future and those who say we should go to a hydrogen-based system. Both is wrong. We need both. We need electricity and hydrogen, or better to say, we need electrons and we need molecules. Simply because electricity is difficult to store, batteries are not really unsuitable in some mobility applications, as shown, airplanes, very large cargo ships. Fuel is needed in some industrial sectors anyway, and hydrocarbons are also needed as a raw material. And therefore, we need both, and both in huge quantities. But first of all, we won't get any renewable hydrogen if we don't increase the installed capacities in renewable power generation. No electricity, no electrolyzer operation, no hydrogen. And here, the gas or other energy storage as long-term energy storage and with thermal power plants as electricity, this is what we have then also for the long-term supply. So both is necessary, and I think this is absolutely necessary to say this. And every hydrogen we can produce in the coming probably 20 years will be urgently needed. But this does not necessarily mean that we should build, for example, fuel cell cars with hydrogen. Because we will need the hydrogen in other sectors much more urgent. In the passenger car, we have, with batteries and electricity, we have a quite good alternative. But we don't have an alternative to produce steel only from electricity. We don't have an opportunity to produce plastics without having hydrocarbons. And we can't fly or put ships for large distances with electricity. So this is a point. We will have a very limited resource for a long while and an expensive resource. Hydrogen will not be cheap, not in the coming 20 years at all. Maybe beyond 2040, 2050, when there is so much surplus renewables and renewables are so cheap. Maybe then also hydrogen becomes very cheap. But in the coming 20, 25 years, there will be always shortages of hydrogen, and therefore the costs are high anyway, but the price will be even higher. Because if there's a shortage in the market, those who produce can take whatever they get. And this is something what have to be kept in mind. This is a background of all these discussions. And it's difficult, because some people really see this as their political agenda, to go into the one or to the other direction. And only if we're doing both and in the best way, in the best combination, then we may get on a good pathway. And this fits very well before we are going for the first coffee break. I mentioned already that we will not meet the 1.5 degrees centigrade target, and probably we will not meet the 2 degrees centigrade target worldwide. So this means all the scenarios also from the United Nations climate panels and so on, they foresee that we are not only have to reduce our fossil fuel consumption and therefore our CO2 emissions, but that we also have to go into negative emissions. Negative emissions simply means taking CO2, which is already in the atmosphere, back and then concentrating on it and bring it back under the earth. And this is such a scenario. So the numbers themselves are not really of major importance in this diagram, but here you have the CO2 emissions per year. So we're approaching here 35, 40 gigatons per year. And we probably will need, or if we would go for a business as usual scenario, so not doing anything, the emissions would increase more and more. If we want to stay below 2 degrees C, we have to follow this black curve here. So this is where we have to get to. And you can see at the beginning, it is still the most feasible way by reducing the use of fossil fuels. Because we can increase efficiency, we can relatively easily change over passenger cars from oil to electricity and so on. But at a certain point of time, it will getting more and more difficult to decarbonize different sectors, and therefore we can see that the expected emissions will stay above the curve, which is acceptable for a 2 degree centigrade target. And this is the reason why, from a certain point onwards, these so-called negative emissions, which are shown here in blue, are necessary, because they are necessary to compensate what is emitted more than acceptable. For example, one of the big problems will still remain agriculture. Agriculture has lots of emissions, especially methane emissions, and this needs to be compensated. And then towards the end of this century, we have to do even significantly more than we still emit, because if we want, then we have at least a chance to maybe reduce the temperature to 2 degrees centigrade increase, or maybe even 1.5 by the end of the century. And therefore, a lot of technologies are discussed. This is just the same diagram with different scenarios. So if we would be able here to reduce the emissions very fast, then no negative emissions would be possible, would be necessary. But this is totally unrealistic. And the later we are with the emission reductions, the more we have to go into these negative emissions. And there are various technologies which are discussed for this. Afforestation and reforestation, so growing more trees gives a certain impact. Bioenergy with carbon capture and storage, growing crops with bioenergy, then burning them, using the energy on the one hand, but taking the CO2, which is emitted in the burning process in high concentration, and then to capture it and to bring it below the earth. So this is called BECCS. Ocean fertilization. Some people think it might be a good idea to put a lot of fertilizers into the oceans, and then the oceans will produce more biomass, and the biomass then captures more CO2. I'm extremely skeptic about these things. So this is what we call something like earth engineering. Because we today have already areas in the world oceans where the oxygen content is extremely low, so low that animals and plants hardly can live, or at least animals hardly can live there. And if we would even accelerate the growth of algae and others in the oceans, I'm not convinced. Then we may do biochar. So this means we put biomass into soils, and the soil can get into chemical reactions and take some of the CO2 from the atmosphere, same as enhanced weathering, crushing minerals, which builds compounds with CO2, or direct air capture. This means we are filtering. We are filtering the CO2 out of the atmosphere by technical means, and then we take it and, for example, we press it into old oil and gas fields. These are the best things we probably have. We fill back the CO2 into the old oil and gas fields. Some countries already see dollars in their eyes. Norway, for example, this is the largest producer of oil and gas in Europe, is selling since decades, and probably since for a certain while longer, fossil fuels to everybody, earning huge amounts of money. Norway is among the richest countries in the world. And now they are offering us their oil and gas fields to capture the CO2, or to store the CO2. So first they earn money with selling the oil and the gas, and then they're earning money by taking the CO2 back. But there are pilot projects starting, building pipelines now going the other direction. Not gas and oil coming from the fields, but sending CO2 into these fields. We will see. The BECCS is one of the technologies which might be important for capturing. We use the plants themselves to capture the CO2, and then we make use of the energy, but we directly take the CO2 and bring it into the geological storage structures is an option. The other one is these direct air capture systems. So these are huge filters. So this is in Iceland, and this system can remove something like 4,000 tons of CO2. And you see it's not small. So 4,000 tons of CO2, this is the emissions of about 600 people in Germany per year. So this system would be sufficient to remove the emissions from today's 600 people. Not really a lot. And it costs a lot of energy and so on. And these are just an explanation. Once again, BECCS, this is these biomass, and then B stands for the biomass, CCS stands for carbon capture and storage, and the DAX is direct air capture, carbon capture and storage. The problem with the ducts is simply technically, because even though the CO2 in the atmosphere makes a lot of trouble, its concentration is only 0.04%. Yeah, so if you filter something with a concentration of 0.04%, you can believe this is not very efficient. And that's the big advantage of the BACs, yeah, because you use the plants to collect the CO2 from this very low concentration from the air. And then when you burn this, then you can have, if you do it in oxy-fuel processes, so with pure oxygen, for example, you can have a very high CO2 concentration, which is much easier than to liquefy or to concentrate or whatever. Yeah, so here, different technologies listed, more for your records. And the big question is, at the end of the day, and this is why there is now one slide missing, nevertheless, the big question is, where do we get with the cost of this? Yeah? And this is something which is extremely important when we discuss all the change in the energy system. There are people who say we will be able to operate these DACS systems, so the direct air capture storage systems, including storing the CO2 below the earth at about 100 euros per ton. Maybe this is achievable. It's not very clear yet. Yeah? Technology is not developed far enough to make really final estimations. But let us assume we are getting down to the 100 euros per ton. And I just mentioned that the price for CO2 in the European trading mechanism just reached 100 euros per ton. Then maybe some will decide not go to saving CO2 emissions. Maybe they're going to use the same processes as today and simply saying, okay, then I take the 100 euro, I have to, the 100 euros to make the negative emissions. So because if this price is the same, why not? So this is something which we should keep in mind, because these are technology game changers. So maybe at a certain point of time we may decide, let the airplane fly on fossil oil, on jet oil, gasoline from fossil oil, because we still have enough of this. And for compensation, we're making the negative emissions. This is something which needs to be discussed, because in some fields it will be quite expensive to do the switch towards CO2-free industries especially. In power generation, we will be cheaper with renewables. This is not the question. We should not operate longer coal power plants, for example, instead of renewable power generation. This will not make sense from an economic point of view at all. But for some industrial processes, production of cement, for example. Cement is causing, I think, 6% of the worldwide CO2 emissions. Germany is doing 2.5% in total. So the worldwide cement industry is emitting 2 to 3 times more than a country like Germany. Extremely difficult, because this is not even the fuels which produce the CO2. It's the raw materials which are used in there, the carbonates, which are raw materials. They emit the CO2. So maybe we will not change this process, but we go for the negative emissions. Not clear yet. There are also other numbers. There are numbers significantly higher. But this is a big problem. And those who are investing, nevertheless, have to think about these things. Because if you invest heavily into a new technology and then such a game changer comes along, not that easy. But beside the price, for sure, we are also discussing how much capacities are there. Also there, the experts have a very wide range in their predictions of the available capacities for negative emissions. I just want to point this out. This is not really now the main thinking, but maybe it could change the thinking very soon.